Hello. In this video, we will present a basic introduction to some intrinsic Python data types and get you started thinking about writing very simple Python programs manipulating those data types. As you learn Python, keep in mind that there are a lot of style issues. Different ways to format your code, different ways to name things. And a lot of those are formalized in a style guide. I've presented the link here. You are welcome to take a look at it. I will be the first to admit that I don't follow all of them. Some of what I do is influenced by other languages that I've learned, and a lot of what I do is influenced by other people's code that I've read. But I encourage you to take a peek at the style guide and get a feel for the way that the maintainers of Python think we might be writing our code. I'm not going to grade you strictly on whether or not you follow this style guide. If I think something is important enough for us to follow, I will mention it and discuss it in the video. So don't worry about memorizing or implementing everything in the style guide. As we saw earlier, we can do some simple Python in the Python interpreter shell, which is an environment generically called REPL, read, evaluate, print, and loop. I have my wonderful Python interpreter shell up and running. I hope you're following along with me. I am also going to use JupyterLab at the same time, bouncing back and forth a little bit just to get you acclimated to both of these environments. We will spend the majority of our time in this class in JupyterLab notebooks, so that's where you should focus your time as well. I won't ask you to do any assignments in the Python interpreter shell. Python is a dynamically typed language. That means when you store something in a variable, the data type of that variable is dynamically defined. That means as the program is running or executing, each time you put something into that variable, Python is reevaluating what data type that variable might be. And that's both good and bad. It has advantages in that there is no compile step that takes time. We don't have to have an ancillary program parsing the code and looking for data types and validating them. And it's definitely a hindrance in some cases because it's easy to get confused and store the wrong data type in a variable, therefore changing its type and then not realizing you've created a problem until farther down the road when you're trying to get the program to become free of bugs. On this slide then, I've just demonstrated a simple example. If I store the number 42 into the variable alpha, the interpreter decides that alpha is an int, which is short for integer. And on the following slide, we just take it a step farther, and we're illustrating rather dramatically the fact that I can change the data type of this variable on the fly, if you will, during execution by simply storing different values in it. And I'm harping on this because it matters a lot, and as a developer we have to think about the data type that we're dealing with, because that tells us what operations can be performed on that variable. So if we don't know, or we're not keeping track of data types, then we're not going to know the capabilities of that variable at that given time. And we'd really like to, and I strongly encourage you not to play this fast and loose with data types. If you decide that alpha is an integer, keep it that way throughout your program. Don't in midstream decide that now it's a good time to store strings in that variable so it should become a string. That will just cause you heartache and grief down the road. Rather create another variable to hold that new data type. You'll be much better off. We're not doing anything resource intensive. Therefore, creating a new data type, creating a new variable rather, midstream in one of our programs is not a hindrance of any kind. I am going to, at this point, just take the code right off the slide. And you can see that on the slide I've shown you what happens when I run it through the REPL environment, the Python interpreter shell. But I am going to take it over to JupyterLab. In JupyterLab, I'm going to create a new notebook, and mine is called untitled2.ipynb because I already have an untitled and an untitled one. Not good file names at all, but I'm just demonstrating concepts here. So I really don't care about the file names at this point. I'll just paste in that code that I took off the slide. And there is a minor correction that has to be made here. The font on the slide doesn't translate perfectly into this environment, so I had to re-enter the double quotes around that string. And if I want to, I can add some programmer documentation by using a pound sign. And we don't usually document to this level. I'm just giving you an idea of what is possible to do. I don't expect you to tell me that you are storing an integer. I think that's self-evident. I do expect some comments, and I'll talk more about those as we go along, but I think you don't have to comment to this level. Okay, remember from a previous video that we can run this by clicking the Run button. And there is output generated because we have a print statement. On the next slide, we'll change direction a little bit and talk about naming conventions. I've demonstrated 4 different styles here. Snake case is all lowercase letters, and words are separated by underscores. That means I can go back to my JupyterLab notebook and I can say hello underscore world equals hello world. And that is a snake case variable name storing a string. If I'm still not sure and I'm feeling my way along, which I do quite often, I can do a print of the type of that variable. I can run that cell, and Python tells me that it is indeed a string, which it shortens to str. Okay, so we've demonstrated how to print the data type of a variable, which I do quite often when I get lost, just to make sure that I have what I think I have. And we've demonstrated the snake case convention. I think you will find that many programmers in Python still use that snake case convention. It's still very popular. Other conventions used by developers mostly in other languages are Hungarian notation with a 3-letter prefix describing the data type of the variable. And that is not to be taken as some special name. That is simply an arbitrary three-letter prefix that is part of the variable name. Okay, it's not a reserved word or anything that is secret. We just decided that int would be the three-letter prefix for integers. And then we have another convention called camel case, where the first letter of each word is capitalized except for the first word. Another style is Pascal case, where the first letter of every word is capitalized, including the first word. I think you're going to find in my code I predominantly use camel case, and that is based on my experience in other languages as a developer. I think that most people who came up through the Python lens, who learned Python as their first language, find that the Python style guide specifies snake case. But again, I'm not grading you on whether or not you learn all of 4 of these cases. I'm grading you on consistency. So if you decide you like snake case and you understand it as Python specific these days and you're in love with it, feel free to use it. If you go to work every day and everyone at your office uses Hungarian notation, fine, go for it. If you like camel case and you like the way my code reads, then adopt camel case. It's completely up to you. Chances are, if you go to work somewhere and they do have you doing development work, you'll probably have to change your style anyway, because every company has slightly different requirements. So whatever I force you to do today, someone else will probably force you to do next year. I'm also curious, as an information technology professional, what other people are doing. So I used a search engine to do some research, quote unquote. I hate to call it that. It's not really research, is it? I found that on Stack Overflow, there is a question that addresses this issue. How do you name things in Python? Now, I posted a link at the bottom of the slide. If you're not familiar with Stack Overflow, it should become one of your best friends very rapidly, because it is a place where you can solve or find the answer to a lot of programming problems. Even in this class, you can find solutions to things that you can't quite figure out, and I encourage you to do that. Notice already the slide, which was published probably a year ago, indicates this question has 737 upvotes, which is a lot on Stack Overflow. That is a lot of positive feedback. But look at it today when I go, it's got 911. So this question is seeing a lot of traffic, even though it was written in 2008, 13, 14 years ago. So it's an old question, but it still gets a lot of traffic because people want to know how to name things. And the accepted answer by the original poster gets 1,001 upvotes. So if you want to know more about what this person thinks, you can go to this URL on Stack Overflow and you can read about the community and their opinion on naming things. Also notice that the link provided in this answer takes you to the Python style guide, which is what I linked to at the beginning of this slideshow. We're all drawing from the same well. But I will reiterate again, I don't have a preference. I'm not demanding that you use any of these conventions. We're all learning. We're feeling our way along. So if you fall in love with snake case, by all means use it. If you fall in love with camel case, by all means use it. I'm fine with that. Back to data types again. Broadly, there are some categories of information that we should understand. We use integers, strings, floating point numbers, Booleans, and complex numbers quite often. Probably not complex as much, but certainly the rest of them. So It's important that you have a basic understanding of how to manipulate those, and I'm sure along with the reading that you've done, we can supplement that here. The syntax is very straightforward if you've done any other language. In this example, very simple. I'm adding two numbers together and printing the result. I am going to grab this code and drag it right back over to JupyterLab. Remember, the beauty of JupyterLab is that I can run individual cells in my notebook. So when I'm discussing a topic, I simply build cell after cell after cell and run them individually. And that makes my presentation very convenient for me and for you to follow, I hope. All I'm doing here then is assigning 123 to one variable, epsilon, assigning 456 to another variable, zeta. Then I'm adding epsilon and zeta together, and I'm assigning that result to iota. Finally, I'm printing out the contents of iota. There shouldn't be any surprise there. 123 plus 456 is 579. Now, let's break this. I've added a typo. In the expression where I'm adding epsilon plus zeta, I mistyped zeta. I put an X on the end of it. And we can glance at this and we can see that there's a problem because it's referencing this zeta X, but we haven't created it yet. It doesn't exist. But we're not going to find that out until we run this cell. Okay. This is an illustration of the concept of an interpreted language in practice, because without a compile step, without compiling this language and checking it for these kind of errors, we don't know there's an error until we execute the language. One of the arguments then against an interpreted language is that you don't know you've made this kind of mistake until you run the code. This is a trivial example of that. There's only 4 lines of code. It's very easy to run it and arrive at that error message. Imagine an application with 100,000 lines of code. We wouldn't know we made this mistake until we traverse to that line of code, and we might not do that until next Tuesday. So, a disadvantage of an interpreted language is that you can't find these kinds of mistakes by running it until you run it through the interpreter. And there's a couple responses to that. A response is, well, let's just get a better tool that tells us we made this mistake before we run the code through the interpreter. And yeah, those tools are available. All right, this is not a brick wall that's holding us up. But in this environment, in JupyterLab, we're stuck. We have to run the code to find out if we made a typo. You, as an information systems professional, are going to need to have opinions on these topics and be able to converse intelligently about these topics. So there is one example of a disadvantage of an interpreted language. Not a showstopper, not necessarily a reason to throw it out, but just something that you need to understand and be aware of. The error message is pretty good. When I ran this cell, it ran the epsilon assignment, it ran the zeta assignment, it tried to compute epsilon plus zeta x, and it cannot do that because there is no zeta x, it doesn't exist, and it gave us a very nice error message. Zeta x is not defined, and that's pretty helpful. It also tells us what line of code contains the error, and we know that it's in the previous cell right above that message, and we can go back and fix that error. In a simple example then, it's fairly easy to backtrack. and solve that problem. In a complex program, it might take you a little bit longer. Let's look at strings for a moment. If we want to add two strings, I am going to grab this code again, right off of the slide. I'm on slide 10. Back to my notebook. Let's add another cell, paste in the code off the slide. Before I talk about that new code, notice that I haven't fixed this problem yet. That cell is still broken. If I run this cell again, okay, I'm going to run the cell with epsilon, zeta, and iota. I still get the error. That cell is still busted. However, if I don't care about that cell anymore, which I don't, I can just go down to the next cell and run that, and it's not going to be affected by any of its predecessors in this case. If all the cells are independent, if they don't depend on each other for anything, if they don't share variables, if they don't build on themselves for any reason, you can just run them separately, which is a heavy advantage of Jupyter Lab, a heavy advantage of these notebooks, if that's the kind of thing you like to do. Because a typical programming environment starts at the top and runs down to the bottom. And this little guy does not do that. This little guy is cell oriented. I am going to run this new cell where I just pasted in the code, and you will see that it runs and it has no care or concern that the previous cell is still broken. We were talking about adding strings. The concept of using the plus sign with two strings is concatenation, not mathematical, not arithmetic addition. In this case, we're adding 1, 2, 3 as a string and 4, 5, 6 as a string, and the sum of those two using a plus sign is not 579, rather it is 1, 2, 3, 4, 5, 6, because it actually concatenates the strings. You can see then the importance as a programmer of understanding data types, because you have to realize that the plus operator behaves differently on string data types than it does on arithmetic data types, integers and floating point numbers. And you also might be curious, when we added these two strings and we stored the result in gamma, we created from whole cloth a variable called gamma, and hopefully you think about using the type function to print and verify for your own good, for your own edification, that it is indeed a string that we created. Mixed mode arithmetic. Mode meaning two different data types in the same expression. Here on this slide, slide 11, we're adding, quote unquote, using a plus sign, a floating point number, beta, and a string, delta, or alpha rather. I will grab this code off the slide and go right over to Jupyter Lab so we can talk about it. Make a new cell, paste it in. As you saw on the slide, this is going to fail, right? There you go. Can only concatenate string to string. Again, a pretty good error message, and it tells us where that took place, what line of code it's in. We can go back and review that code and decide what we did wrong. In this case, it's a logic error, and it is logically incorrect to try to add a string and a number. And that is a behavior of Python. Python does not let you do that. I could easily find you a language that would let you do that if you thought that made sense. We could add strings and numbers together, but Python does not let you do that. Okay, so we're exposing you to different ways to think about problems, different data types. The Boolean data type. Boolean means that this is the kind of variable that can only assume either true or false values. It can't be anything else. It can't be a numeric, strictly numeric. It can't be a string. And the way you create one of those is by storing capital TRUE in that variable, and it becomes a Boolean. If I grab this code off the slide, whoops, I deleted it. Get myself a new cell. And we saw from the slide that this is going to fail because lowercase true is not recognized by the interpreter. So the only way to specify a logically true constant value is with a capital T. And hopefully then you're curious enough to print out the type of zeta. We expect that to be Boolean, but we're not going to get there because this fails. We still can't do it no matter how hard we want to do it. And I can just comment that line out to make it go away, put a little pound sign in front of it. Now it's gone. It's a comment. It's ignored by the interpreter. And you can see that I got bool. If I print zeta, you probably can guess what I'm going to get there. True. Let's be more curious. Can I add an int and a Boolean? Can I use the plus operator, the add operator, on those two data types? Is that mixed mode arithmetic possible? Interesting. Let's create an integer. Delta equals 42. And then I'm out of Greek letters. Omega equals delta plus zeta. We have to stop and take a look at that expression and think about what it's going on there. We're doing a plus operation. You can call it addition if you like. Delta is going to be an integer. Whoa, I wrote that wrong. That's not Python, sorry. That's Java. Okay, that's more like it. Delta equals 42, and that will implicitly become an integer. Delta will become an integer. Zeta I know is a Boolean because I initialized it to true. Can I do this? Will this run or will this fail miserably because it is an invalid form of mixed mode arithmetic? Will this work? Well, we live in this wonderful sandbox, so all I have to do to find out if I'm right or wrong is run my code. I'm not going to destroy anything or melt anything or short circuit any electrical device. That's one of the things about most software projects is that the sandbox is very is fun to play in. What did I get? Well, I didn't get an error. Okay, it ran this line of code. It executed this mixed mode arithmetic operation. It did a plus operation on a Boolean and an integer. Well, now we're kind of surprised by that because that didn't work up here. We could not do mixed mode arithmetic on a string and an integer, but we can do mixed mode arithmetic on a Boolean and integer. Okay, we're learning a lot. The next thing we're curious about is what in the world is the result of that, and what in the world is the data type that results from that? Let's find out. Okay, I started with 42. I added zeta, which I know had the value true in it. and I got 43. How about that? How about that? What did it do? Well, it converted zeta to an integer, and it converted the Boolean value true to a 1 and added that 1 to 42, and that gave us 43. 43 is an integer, therefore omega is an integer. And that's the result of all that gobbledygook. I'm throwing a lot at you in a hurry. I'm interested in your ability to figure out these kind of problems and understand a little bit about what's going on behind the scenes, but I think it's going to take a lot of practice for you to be very proficient at this, so don't stress out right away. There's what I just did. So you should be able to look at this eventually and explain to yourself and explain to me why the answer is 2. Zeta is a Boolean, and we stored true in that Boolean, which really behind the scenes is just a 1. A true is 1, a false is 0, and then we add 1, so that essentially ends up being 1 plus 1, which of course is 2. So behind the scenes, it's really not mixed mode arithmetic, if you want to know the truth. It's really adding 2 integers. Okay, one of the very quirky things about this language relative to most other mainstream languages is that I can just jam a number of almost any size into an integer. This is unique. Here's a slide from a previous presentation that you saw earlier in this module. We talked about the popularity of Python, measuring it against other quote-unquote popular programming languages. And we saw that Python consistently ranked very highly in these 2 surveys. But I've brought you back to this slide because the ability to jam these excessively large values into an integer is not anything that any of these other languages can do on these slides. You just can't do. You can't do it with C or Java or C++ or C# or Visual Basic. Not going to happen. So in most languages, we are very concerned about the upper bounds and the lower bounds of a lot of these data types. But unique to Python in a lot of ways is that there's a practical upper bound somewhere, but it's not really defined. If you look in the literature, it says that an integer can be whatever you want it to be, and here I just made up some humongous number and stored it, and Python was happy to do that. That's a ready-made syntax error in most mainstream languages. Okay, how does that affect us right now? It's just a quirk. It's just something to give us a better feel for what this language does. It's not something that we're going to make any use of right now. I will also say that this is going to be incredibly slow relative to most other languages. The ability to do this comes with a big boat anchor, and that is speed. So if you think you're going to compute anything of any significance that requires this kind of numeric value, you're going to pay a price in execution time. Not saying you can't do it, just be aware that it will cost you. Circling back again, we've talked about data types quite a bit already, and you can see that in this example, I just store the same value except different data types that look kind of the same. And then the interpreter dynamically adjusts the data type of that variable. So there's another example of dynamic typing. I want to discourage you from doing this. I do not recommend this under any circumstances. So let me find my way back to the browser here. This is a bad idea because the programmer brain is very comfortable thinking about a variable having a data type. The programmer brain is not comfortable with the data type of that variable constantly changing. Let me fix the double quotes around that 42. So while you can do this, you're much better off making a new variable each time. Now those are terrible names, but I'm just illustrating new variables. So if you store a value in a variable, I would recommend continuing to store that same type of variable in that type of value, in that variable. Don't flip around. Don't play fast and loose with data types. It's just not a good idea. Oh, I got an error. What did I do? Oh, this should be 3x's here. There we go. Python knows about other numeric bases. If you're familiar with hex or binary or octal, that's great. I won't be talking about it in this class. It's usually more of a computer science or engineering type issue, but you are exposed to it here. I'm not going to ask you to do manipulation of numbers and other bases. Sometimes we have a need to convert from one type to another explicitly to force that conversion to take place. And there are functions available in Python to do just that. So we can convert something to a string, or we can convert something to an integer, and it's easy to do. Once again, I will borrow what's on the slide. I'm on slide 18. And I'll fix the quotes again. Those blasted quotes are still in the way. Okay. We've created an integer called x. We've created something called y. We're not quite sure yet what it is. But I want to add x to 123, and I'm really going out of my way and bending over backwards and twisting myself in a pretzel to do this. But I'm illustrating the fact that I can take a string, which is anything in quotes, and convert it to an integer, and then add that to some other integer. So that actually does an arithmetic add. However, look, I can break this very easily. What if I just wasn't paying attention and I put a value in that string that cannot logically be converted to an integer, 123 exclamation point. Can that become an integer? Nope. And the error here is invalid literal, meaning that whatever is in that string, I'm asking Python to convert it to an integer, and I can't do it because there is no conversion of an exclamation point to an integer. Here's your interpreted language issue again, and when we ran the program, we got an error because what we're trying to do is not logical. It's not possible to do. We can read from the keyboard using the input function, and I'm not going to do much of this either. If we need data, we'll get it from a file, or we will just hard code it into our program. So we won't be doing a lot of keyboard input stuff. It just slows us down and makes things makes a lot of drudgery work having to type data in over and over. But to provide a demonstration of it is fine. And I'll take a cell in my notebook and I will paste in the code off the slide. Luckily, no quotes to fix here. So the first line of this cell stops execution of the program, waits for you to type something in, and then stores that in Z. Whatever you type goes into the variable Z. And then I print out Z, and then I print out the data type of Z. And as you might expect, here we go. The cell now sprouts a little text box waiting for you to type. So I can type in hello world. I can press enter. And Python took the keyboard input, stored it into the string Z, then printed it back out for us. Not a good idea for developing anything of any substance because you don't want to spend half of your day typing in data trying to debug a program. We won't do too much of that. Everything that comes in from the keyboard is a string. All right. So if you want keyboard input to be numeric, you have to read it in as a string and then convert it to an integer. We could go back to our Jupyter Lab notebook and we could say Z equals input and then Z numeric equals int of Z. So by calling the int function on Z, we can convert it to an integer. There's a useful application of that explicit type conversion, the int function. And that, of course, is only going to work if whatever I typed in can be converted to an integer. If I type in a string of characters, if I type in A, B, C, that's going to fail when it tries to do that type conversion. There it goes. Invalid literal, the same error we got before when we tried to convert an exclamation point to an integer. Here's an exercise for you to do. Read two strings from the keyboard. I'm sorry, it says things. Read two things from the keyboard, convert them to integers, and add them together. It's a simple extension of what I've been doing here in the cells. Instead of one input statement, you're going to have two. And then print the result. I added a little caveat. What happens if the input is A, B, C, and X, Y, Z, meaning what happens if the input is invalid and cannot be converted to integer. And as you can imagine, you're going to get that error when you run that program. So I encourage you to take a moment, start from scratch, copy paste code that I've provided for you in the cells of the Jupyter Lab notebook and write up that little program into its own new cell. Get it to work. That'll give you some confidence that you can write a little Python program. Okay, when we get more complex, we have lots of things in what we call the current scope. There's a lot of variables flying around, and sometimes we might lose track, or we might want to query that list of things to make sure that we have what we think we have. And the way we can see the list of things is by doing a dir. So dir is a function, and it will return to us all the things that we have created to that point, plus some built-in things that we don't even know about. So let's go back to our cell. Let's get a brand new cell in Jupyter Lab, and let's say alpha equals 42. We've done that before. And let's say print dir. Whoops, I got a couple of extra parens there. How about that? So the first line of code creates an integer. That integer goes into the context, or I refer to it as the environment. And then this print function tells us what we have in our environment. There it is. And you're going to see a lot of things in there that you recognize. Let me see, do I find alpha in there? There he is right there. There's alpha. But also notice beta, delta, epsilon, hello world, iota, omega, x, 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 because every time we did something in a preceding cell, that was added to our environment. So we can reference all of these things that we did earlier. Like when I print XX, I get 42, because if you scroll up a little bit higher, there's where I put 42 into XX right there in a previous cell. Your responsibility as a developer is to keep track of what you've done. What are all the variables I've added to the environment as I execute the cells? You can see that it gets complicated. Another variation on this theme is the vars function. Not only does it give you the name of the variables in your environment, it tells you their values as well. If I go back over to Jupyter Lab and say print vars, I'm going to see that there's much more information here because it's giving me the value of each one of those variables that I worked so hard to build in all of those cells. And there's alpha right there, 42. Now, this thing that vars gives us is called a dictionary, but we're not ready to talk about that yet. Let's make sure of that. Maybe I'm wrong. Print type vars. Can I do that? There it is right there. Now, without the parens, it tells me it's a built-in function or method. Okay, so it knows what vars is. What if I put parentheses after it? Print type vars, open close paren. Now, there it is. It's a dictionary. Next week we'll talk about dictionaries, and they will become an integral part of your life for the remainder of the course. But not yet. And there's a reiteration of what I just said. I got ahead of myself, I got excited, I told you about dictionaries, and there it is on the slide. Now this syntax is an extremely useful dictionary access tool that, again, we'll talk about in a little bit. So I'm not going to address that now. Finally, I have linked to a 7-question Python quiz. I'm going to leave it up to you, and I suggest that you take the quiz. Now, most of these answers you can solve, if you don't already know, by writing a little bit of code in a cell. So if you're not sure what the result is of an expression or how to do what the quiz question references, you can cobble up a little bit of code, try to figure out the answer, and it will be extremely helpful to you. A lot of them, or some of them, also you may know off the top of your head, like this one's pretty easy based on the discussion that we've already had about maximum values stored in integers. I harped on that for about 5 minutes. I encourage you to take the quiz and see what you get. It gives you the answers at the end of each question, and you can learn a lot about the ins and outs of basic Python data types. And that brings us to the end of this presentation. Thank you.